Okay, so I'll try my best to, for the people at the back, is the hood is running very loud, so I'll try my best. So let's go and look at might be one of the multiple choices will ask you what does VSEPR stand for, then we'll give you 4 options. So you have to know what the abbreviations are. Yeah, what the abbreviations are. So the abbreviation is, as you can see here, guys, V stand for valence, S for shell, E for electron, and P for pair, and R for what I heard the correct answer for repulsion. So this is VSEPR. Well, the VSEPR is nothing else than just a technique or a procedure or a method to determine the shape of a molecule. Why is the shape of the molecule is very important? Well, it turns out to be a lot of chemical and physical properties. A lot of chemical, thank you. A lot of chemical and physical properties will be determined or will be dependent on the will depend on the thank you very much, thank you, will depend on the physical and chemical properties will depend on the shape of the molecule. In the sense, I can determine from the chemical and physical properties, this is chemical and physical properties first, such as A, resonance of a molecule, B, isomerism, C, the polarity, correct? Those are physical and chemical properties. Is very important. What is resonance? Somebody will tell me what resonance is? Remember that? Resonance, did you cover it in the lecture? Well, the resonance is the migration of the bi-bonding of the double bond through the molecule. Correct? That's what resonance is. VSEPR will give you the idea about this resonance. Correct? Migration of the double bond through a molecule. For example, if I have the benzene ring have three double bond. 1, 2, 3. This is 1, 2, 3. 3 double bond. They can migrate. So now the one is migrating to this one here will be here, 2, 3. So now the one here is 2 here, 3 here. This is called resonance. So resonance is the migration of a double bond through a molecule. The same thing if I have nitrate. Nitrate is looking like this. And that's oxygen. That's oxygen, negative. That's another oxygen. It's negative and nitrogen is positive. This is number 1, the double bond. Now the double bond can be moved to the second oxygen. So you have this one here can go. That's what you mean by resonance. So this one can go to nitrogen, oxygen here. Double bond is now here. Okay. Negative, negative, and this is positive. Okay, that's positive here. So then the double bond is in this position, correct? Now it's in this position, second oxygen, and it can goes further and it can move around. So we can do this one here. Always make double arrow, those are structure, the same structure, but the migration, the dislocation. Dislocation means the double bond is not located in one location. It moves around the molecule. So now I have, this is oxygen here, negative. This is oxygen here, negative, positive nitrogen, and now the double bonds here. So we always double arrow means migration of the double bond from this oxygen to this oxygen to the other oxygen. That's what we call it, resonance. Are you following me here? Resonance. That's what we call resonance. Isomerism, the VSEPR will give us idea of the isomerism. So this the molecule can have the same molecular the same molecular mass, the same molecular structure. However, in the space, the orientation is different. In the space, orientation is different. So I can give you one of those here, example of isomerism. Can I take this one out? Can I take this one out? So that's what means. That's first resonance. VSEPR will give you information about this. Correct? Then isomerism, then I'll give you an example here. The arrangement of the atoms is totally different, but we have the same number of molecule, correct? We have the same number of molecules. So, can I take this one here out? Can I take it out? Everybody has it? So now I can look at the two molecules here with this one here, CH3O, CH3 versus CH3, CH2, OH. This is an ether, this is an alcohol. This is the ethanol, and the other one, the methoxy ether, methoxy ether or methyl methoxy ether, or called just dimethyl, the common name, dimethyl ether. So, but let's look at the number molecular. How many carbons we have here? 2. How many hydrogens? 6. How many oxygen? Is 1. How about here? How many carbon? 2. How many hydrogen? How many oxygen? Are those the same? That's what we call isomerism. Those are isomers. So the rearrangement in the space is totally different, and therefore that will lead to different physical and chemical properties. This is non-polar. This is polar, meaning this is not soluble, insoluble in H2O. Okay, this is soluble in H2O. And therefore even the boiling point, the melting point, the freezing point, all this will be different. But the molecular weight is the same, the molecular structure is the same. This is here molecular structure, the same thing. But then when you rearrangement in the space, you get totally different. There's no in common. 2 different groups, one alcohol group and the other one an ether group. That's what we call isomers. Correct? And the next one is VSEPR can offer for us the something called polarity of a molecule. Polarity of a molecule means this molecule can be conducting electricity and soluble in a polar solvent such as H2O. So let me write about this. First asking, everything is here. Can I take this one out? Can I take this one out? So you know what isomers are now. So, and there are many molecules like this. They will have the same molecular structure, but they differ in the space. Rearrangement space will be different, leads to different groups of different physical and chemical properties. Alcohols are very reactive. Ethers are very inreactive. Correct? Alcohol ethers are very low ignition point, so they can't really, somebody will smoke outside and they are heavier than alcohol, they move like snake. And see the cigarette, somebody smoking outside will burn the whole thing in his face. He will be wondering from where is the fire. Ethers are very heavier, more dense than air, and then alcohol, so they can travel like snakes, and therefore, but they are not polar. The good thing, they are not polar. But alcohols are polar, and therefore they have higher boiling point than ethers. So now let's look at the last point we said is polarity. Well, it turns out polarity from the VSEPR. VSEPR is telling us a story about any time a central atom, this is here it is. This is hydrogen. This we call it terminal atom. Terminal atom. This is another terminal atom. The presence of the lone pair is forcing the molecule to be polar. So that any molecule that has a central atom of its lose that structure, this molecule will be polar. Period. Correct? Now any molecule that has similar, no lone pair, but similar terminal atom. So this is will tell us, the VSEPR will tell us, well, this is oxygen and this is oxygen. So this is symmetrical molecule is not polar. All this polarity means is soluble in a polar solvent that conduct electricity. Polarity always conduction of what? Electricity, flow of electrons from one side to another side, valence electrons, that's what it meant. Okay, so this is not polar, not polar. But if I change the oxygen to sulfur like this, here it is, this is polar now. Why? Because this is not identical with this. The dipole will be, the oxygen is more electronegative, will be pulling this way. Carbon is almost the same, identical, so it will be no pulling, the same electronegativity difference. Remember in the lecture it took a long time ago in survey of chemistry 1 or so, that's electronegativity. The difference between electronegativity will give you the direction of the dipole. Oxygen is 3.5 electronegative, and this is, I think, is 2.5. There's a difference. Oxygen is more, so the valence electron of carbon will be pulled this way here. The pulling starts from the valence electrons of carbon towards the oxygen, and this one no pulling because they have the same electronegative number, 2.1 or 2.5. I don't know, but they are similar, so there will be no pulling here. But the whole molecule is polar because the pulling will be this way. But here, this one will pull this way. This one will pull this way. Oxygen is more polar than carbon. Those identical dipoles will give you the direction of the pulling of those valence electron of the central atom towards the more electronegative atom, and those same values but different what? Direction. So they cancel themselves out. So the dipole, the net dipole here, the net difference in electronegativity is 0. Here is not. Here is 3.5 minus 2.5 is 1.0. So there is a dipole here, it's polar, but here is 0 because the same strength, opposite direction, they cancel themselves out. Thus, VSEPR is giving us those type of information. Okay, guys? So, what's the basis of VSEPR? VSEPR is really depending on Lewis dot structure. if you have a wrong Lewis dot structure, you will have a wrong shape of the molecule. Correct? Wrong shape of the molecule. So, can I take this one out? Everybody has it. So, any question you have, guys? Any question? Any question? So let's take this one out and look at the basis of, so VSEPR depends on Lewis dot structure. So incorrect Lewis dot structure will lead to incorrect shape of the molecule. This is very important. So you have to have this one, the Lewis dot structure, correct in order to have this VSEPR shape correct. You have to have Lewis dot structure correct. So now we said this, and we have to differentiate between two items. We have molecular shape versus electronic shape, or electron geometry versus molecular geometry. So can I take this one out? And then we'll go for the procedure. We'll go for doing the Lewis dot structure and then make those models. So can I take this one out? Everybody has it? Everybody has? Okay, let's have this one here, and then let's look at, and that's those files. I add them for you so you can just go and click on the link. We have electron or electronic geometry or shape versus molecular geometry or shape. So the question is, what's the difference between those two? Well, some of them will consider the double, the lone pair on the Lewis dot structure. Some of them will ignore it. So the molecular geometry here does not consider the lone pair in the lone pairs here. Here it does consider the lone pair or the lone pairs. I give an example of this. An example. Let's do an example here. This is an example. Let's take H2O. That's very nice to see H2O. H2O Lewis dot structure looks like this. This is oxygen. Hydrogen always in Lewis dot structure. I'm not going through Lewis dot structure. You have covered this one here in the lecture, I hope. Okay. So this is central atom here. Okay, central atom. And I said octet rule, you have 4 elements. You have to watch 4 elements for octet rule: carbon, nitrogen, oxygen, fluorine. You have to consider those for octet rule. They have surrounding them bonding or non-bonding 8. So 8 VEs, valence electrons, has to be around those 4 elements. All the other elements in periodic table, the non-metal here, the covalent bonds, they might exceed the octet rule. But oxygen is part of the CNOF. It has to have 8. Let's count those 8. And here they are. 2 sets of non-bonding. 1, 2, 3, 4. Those are non-bonding. Non-bonding VEs, or called VEs, valence electrons, are called what? Lone pair. Lone pairs. Lone pair set. And the other one the same thing. 1, 2, 3, 4, 5, 6. That's bonding. One sigma bond, one single bond. 7 and 8. So oxygen is satisfying the octet rule. Hydrogen is not. Hydrogen is always will be terminal and bound because it has only one single electron. It cannot be in the middle. So always at the edge, at the terminal position. Correct? But those are the 4 ones we have to watch to justify the octet rule 8. Okay. Now, I look at the electron geometry. The electron geometry is telling us I have 4 units. So regardless, whatever is double bond or triple bond, they call it in your work set domain. Whatever you have here, let me just take. So I have 1. This is 1 unit. This is 2nd unit. That's the 3rd unit. Okay, this is 1st. This is 2nd. This is 3rd, and this is 4th. So the electron geometry is saying this one has 4 units. This one has 4 units. Okay. So with this mind, they consider what? The lone pair. So the electron geometry of this, of H2O, it's A. If you put this on A and this is X, correct? The terminal is X, and this is A central. Lone pair is E. E. So the A X2 E2, 2 lone pairs and 2 terminals. That's the VSEPR code or VSEPR formula. The VSEPR code. With the help of this, I can determine what? I can determine the shape of the molecule. The electronic or electron geometry or shape, I have to consider all those 4. 2 plus 2 makes I have 4 groups. So this one here, according to this electron geometry of H2O, is tetrahedral. 4 units. Tetrahedral. Here in the molecular one, well, I ignore. I look at this like this. Okay, I ignore those pair of the lone pairs. The lone pairs is not considered. So how does it look like? Well, it said the shape of it is bent. You see the difference here? There you have to consider all the lone pair sets. Therefore, you have 4 units. Here you consider like it has only 2 units. You ignore the lone pair. So it is bent. Everybody's following? So that's the difference between the electron geometry and molecular geometry. Molecular geometry does not consider the lone pair set, while the electron geometry does compare that. So if you look, you have this, everybody has this. Can I take it out? So now, today we'll have the opportunity to look into, I'm not going to the Lewis dot structure. You covered this one here in the lecture. If you have any question, just email me. I will be more than happy, because that will be out of the scope of the experiment, because Lewis dot structure is a lecture by itself, or 2 lectures by themselves. Correct? So can I take this one out? So you will get a recording of this. Don't worry. So let's take this one out, and let's look into this one here, the procedure. So I'm looking into the procedure here, and what those those are the resonance. Can you see those are resonance? The double bond is moving around. So the double bond here is the double bond. So it moves around. So here it is, 1 double bond, and then it goes. That's the resonance here. You can look at those example. Correct. So now, we will come here and then we'll have those type of regions here, and we'll have the bond angle and the example, and determine if they are polar or non-polar, correct? So here it is, and we'll take, that's this is the ones you need it for quiz number 5. You have to bring this one out, and there is another one here. Look at this. There is another one here, and tell you what's the difference between, I think, a number of electron pairs. They give you a number of electron pairs, correct? The yellow one are the lone pairs here. The lone pairs, non-bonding one, correct? So, and here it is, part 1. We have to look into those. We will do all those, and then we will be done with the whole experiment. So at least we can do a couple of those, and then you tell me. So the total valence electrons is very important. We can check if we have all the numbers are there or not, or is some missing or more. So if some missing, where they are. If they are more, then we have to get rid of the extra. So this is like a controlling one, and determining if we have to force the molecule to have double bond or triple bond or single bond, correct? So this is there are two things here you have to look. You have to look into this here. So in the top, number 1, electron geometry, correct? Electron geometry does consider what? The lone pair. So we have tetrahedral. This is tetrahedral, correct? However, the molecular geometry or shape, the molecular geometry does not consider this lone pair. Discarded. This just looks like it, like this is triangle here, correct? And the top of the nitrogen is, like a pyramid for all those. Trigonal pyramidal. Okay, guys, that's the molecular one. Now we are not interested in the electronic, or electron geometry. But if you asked, you have to consider it. You have 4 zones. That's a tetrahedral, correct? And I put for you inside the iCollege. Let me just. So you have both of those, and let me just go for iCollege here. I put for you VSEPR chart. Let me take some out. This one here is I think by far better than yours inside your procedure. So your lab procedure, I think I took this one here from the web. Show you is much better. Then it's give you electron pair geometry, and it give you the molecular geometry. So from here, that's in iCollege, guys. That's in iCollege. So you have to print this one here. Good. That's the molecular shape or geometry, and this is the electron shape or geometry. Correct, guys? So, and you can see how they look like. Everybody's following here. So you might have to print this one out for quiz, last quiz number 5. Okay, guys? I think it will not come to very, very complex ones, because then it will, this one here is maximum it can go, but then you have a lot of other stuff, so we'll not go in depth. But this is the one. Is really is a very good, by far, a chart that's showing us molecular geometry versus electron geometry, electron pair geometry. So let's do our own now. Okay, guys, we are going back to look into our own, and then we'll do what? We'll do the building of this block here, this the molecule, correct? So let's have this one ready here. Okay, we'll do all of us as much as we can. What's that? Any question? Those are not treated as a toy, guys. Those are a model, not a toy. So make sure that you don't lose them, because some students will be using them for the other classes, please. So, everybody got that? Okay, so let's do this one here now. And whisper chart here. That's the experiment here, so I'm taking this one out. And let's do ICl4 minus. That's an anion. So what we call this one here is this is iodine tetrachlorate, okay, or tetrachloride ion. So how about number of electrons, total number of electrons? Somebody will tell me how to calculate total valence electrons here. First of all, we have to fill this one here. Here, guys, what's the number here? What's the number here? What's the total valence electrons? Well, it turns out the iodine valence electron is 7. Chlorine, for 4 of them, 4 multiplied by 7. And then you have a negative ion, which is, a negative ion should be added. Negative ion, if it's positive, has to be subtracted. Negative ion means plus 1. It's at minus 1, correct? So it's plus 1. So you have 7, 28, and plus 1. So this is 36. The sum is 36 valence electrons. So this one here will be, okay, so let me take this one here. So this is 36. Okay, now pairs of bonding electron on the central atom. Well, we have to do Lewis dot structure of it. So Lewis dot structure of this will be looking like this. The iodine is 1, and you have the chlorine all over the place. All over the place, correct? So 7 of electrons of chlorine here. 7, and here's 7. So the iodine is missing out of the 7. Look, guys, there. The iodine is missing out of this one here. Those are 4. Correct? Those are 4 because it has another we added. It has 3 plus 1, the ion, the negative ion. So it will have 2 sets. 2, 1, and one from the ion. Here it is. This is negative from negative charge. Okay, guys. Therefore, here's the negative. So this is the Lewis dot structure of it. So now let's do this one here together. Let's do that's not there is no space for it, but there is no space, but we really need how many sets of non-bonding pairs? We have 2 sets, correct? 2 sets. One is here and one is here. 2 sets of lone pair, okay, and 4 sets of single bonds. So now if I have, looking at the electron one, I will have A, this is A, central atom. All those are B's, B, 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 and then I have E1 lone pair, E2 lone pair. So I have the formula. It has to be somewhere. I might work this one out to see. You have to have the formula there. So you have A, B4, E2. If I consider both for electron geometry, this is 6 units, correct? 6 units, this is octahedral. Okay, guys? This is an octahedral if that's for this electron shape or geometry. So it's octahedral. Why? Because it has 2 plus 4 is 6 units, or zones or domains. They are the same, or groups or units or zone, whatever you call them, they are the same. 4 sets of single bond and 2 sets of lone pair. How many in total? The total is 6. Total is what? 6. Okay, guys? So the electron geometry is octahedral. Now the other one, if you don't consider those two here, then will be the molecular shape. Then you can come and look at the chart here. Okay, guys, everybody has this? Everybody has this? Yeah, please have this. Then we'll go, because I have to switch to show you where will be. That's AB4E2. AB4, or in your stuff here, I apologize, not B, but sometimes they put the P here is X. So let's put the same thing you have there. They put it as X, so it does not really matter. So let's put this one here as X. So you have 4 X's here, X, 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 and here X. So 4X. So, and 2 lone pair sets, correct? So the electron geometry is 6 group, 6 domains, 6 zones. Those, you add them up, 2 plus 4, 6 is octahedral. But how about if I have 4 single bonds and 2 sets of lone pair? Well, you don't have to memorize. I don't think so they will give you something in the lab like this, very complex. But at least we'll be able to do it. So can I take this one out? So we know AX4E2 and we know the structure of it. So let's look at the shape of that here. Let's look at the shape here, and then let's look at this. Where this might be, where might be? We have an octahedral. But this octahedral has how many? It has 2 sets of lone pair. Where is it? Come on, guys, don't let me down. Those are the 6 here. E, A, central atom, and X, 6, correct? This one here, A, X5, E1. This one here. This one here, AX4, E2. That's ours, correct? Then the molecular is square planar. Are you following here? So, yes.
Okay, so why is it because that's how many extra electrons are for the...
No, that when we did the loose dot structure, therefore it's loose dot structure is really the core of the VSEPR topic. So it came like this, correct? Here's your X, whatever this chlorine, here X, here X, here X, and then you have 2 sets of lone pair, and the one here from the charge, this one from the charge, so the negative here. So then what you have to do is just make a note of those here. Say this is your A, central atoms are always A. This is your whatever terminal is X, all those X's, and the lone pair is E. So you have AX4, you have 1, 2, 3, 4. How many sets of lone pair? This is 1, and this is 1. 4 here, and E2. Then you come and look at the chart. You look at the chart here. Those blue bubbles there, those are the lone pair. Those bubbles here. Like this one here, look, this is 6, correct? But this is A, central atom. How many of this? X2, and E how many? 4, correct? That's linear. And let's do this one here together. A and X how many? 3. And E how many? 3. That's T shape. Okay, guys? Makes sense? Makes sense? You need this one here because this one here you can, but you can determine between electron and versus molecule. The electron does not care. It does contribute. Those are 6. So electron will tell you this is octahedral. Here it is. That's electron. That's octahedral. 6. That's octahedral. Does not differentiate between those lone pairs or non-lone pairs. Okay, guys? Okay, so this is number 1. Let's do it together. Let's do it together and hope for the best. We have 2 sets. Can we do it together? Well, I'm trying to. So we have 4, but it does not have. We can do 6. Can we do the 6? Can somebody more initiative? So more think. So 1, 2, 3. Maybe this one is. So here it is. Here it is. The longer one, that's a single bond. The shorter one is double bond. The one is see here. This is what? This is longer one. This single bond. Half of it is double bond. The smallest one is the triple bond. So we have 4 single bonds. 4 single bonds. 4 longer bond. 2. Okay, so let's get this one here. So I hope you can do it. So well, I don't have 2 of. Somebody got 6. It's very hard for this. You can skip the model of this because I don't have a lone pair here. Somebody has the lone pair. I don't have even lone pair here. The lone pair will be looking the one like a small tiny, like a leaf, beige leaf, like a leaf, a plastic. Yeah, that's a lone pair. But you have 2 lone pairs. Mine, I have here 1 lone pair. I can't have 2. Somebody has 6. 2 lone pair. You got 1. Okay, so I'm trying to get. This is 1, 2, 3, 4. That's 5. So 1, 2, 3, 4. I don't have any of those, by the way. So I really apologize. I don't have even a lone pair. I don't have lone pairs. I don't have one with the 6. So if you have it, you can make a picture of it. And then you don't have it. You have it. Did you have a? But you don't have. You have to take 2 out and then put lone pair. But you have to do lone pair of that. Lone pair as the one with the leaf, like the one she has in her hand here. The leaf one. You have to put, instead of the tall one, the leaf one. Yes. Well, I don't see it. No, you have to have 4 and 2, 6. She has 6, but yeah. Can you bring this one here? So then we have to document this one here.
One more is missing.
One is more. I need 1 or more of this. Here, you can take this one here. Okay, so may I have your attention here? Make a picture of this. This is here. Can you? This is 4. 1, 2, 3, 4. The iodine in the middle. Those are the chlorine. You have to put the bubbles for the iodine, whatever the bubbles. I mean the bubble. 4 of those. Or let's take the red. I have the red one. So here it is, guys. The first one. Okay, guys. Here, guys, may I have your attention here, guys? Can you see it? Here it is, guys. We have two lone pairs. Those are the flat one. Those are lone pairs. 4 chlorine atom and 1 iodine atom. So
You don't have green one.
no, the green one I have. No, the green one you cannot. The green one is small size. It does not. You cannot put the green. Why? Because the green is small one. Iodine is bigger than the chlorine. Iodine, size-wise, atomic mass is bigger. You cannot. That's not representing iodine. I put them the same. I mean, the same size. You have to look at the size too. So this is a central atom, 4 X's, 4 terminals, and 2 lone pair, 2 E's. Have they got that one here? Have they got this here? Trying to get this one here at least. And you have 2. So, and this is the molecule here. So, okay, guys. So, take a picture of this, and then you can include the picture inside your discussion. So, I will keep this. Yeah, but that's not really true. That's not true. Why? Because the iodine is and chlorine.
Chlorine, yeah, iodine is in the middle.
Yeah, iodine is in the middle. The chlorine is smaller, but not that small. But anyway, so anyway,
Just follow the colors for the elements.
yeah, that's fine. That's fine. That's fine. Iodine is bigger. Yeah. So here it is. You can take yours. Okay, so take a picture of this. I have here's this one's almost empty. There's nothing there. So anyway, so yeah, sorry about this. Thank you. Okay, guys. Next, what's next? So the bond angle is, you can get this one here from, because the more you have lone pair on the central atom, the more squeezed the atom is. Let me just make a note of this. Is the molecule polar? Yes or no? Yes, it has 2 sets of lone pair. Now I want you to look at this. Oops, that's not Excel, but we want to get our that's not Excel. I need the Word. So here it is. Okay, guys, here it is. The more lone pair on the central atom you have, the more polar the more polar the compound. I have here. Look at this, guys, here. That's methane or carbon tetrahydride. Carbon tetrahydride or methane. That's CH4. So this is carbon tetrahydride. Yes.
On the key, it says it's not polar. In the table that's
In the table is not polar.
It says no. Square flame, that's what we just did. Is that now folder?
No, but square planar, if the whole X are the same and you have no lone pair, no, it should be. It should be. That's something, a typo. That's a typo. That's a typo. That's a typo. Here, guys, look, listen, guys. Listen, guys. Listen, guys. Listen, guys. I will start here, guys. Look. This is here. This is ammonium, correct? Or whatever this is. This is, I will put ammonia here. Look at this, guys. One set of lone pair. This one no lone pair. Correct?
No, they're all 4 bonds.
This is one set. Correct, guys? This is 2 sets. 1 and 2. Correct? Those 2 sets. Now the question is, which one is polar? H2O or ammonia? So this is polar. And this is polar. Which is more polar? Which is more polar, guys? H2O or ammonia? No. Here it is. Guys, listen. The more lone pair, the more lone pairs on the central atom, the more polar the compound. Okay, guys? This is true. Are you following me here? And if you read something has a lone pair or tell you not polar, that's not true. Any central atom that's carry out a lone pair has to be polar. Blindly, you don't have to look at the polarity or calculate the difference between electronegativity. Are you following me here? This compound is polar. It has 1 set. This one is polar, has 2 sets. Now how about if I have a theoretical compound which is inside, say X and then Y, 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 and it has 3 sets of lone pairs. So let's take the Y here out. It has something like this. So which will be polar from all those 3? So this one out. So here it is. I have 3 sets now, 3 sets of lone pair. Which will be more polar? This compound will have more polarity, is more polar than H2O, than ammonia. The more lone pairs on the central atom you have, that will force the polarity to be high. Everyone's following? Now, the opposite effect of this lone pair is, this is 109, tetrahedral, 109. The angle is, okay guys, here it is. This is 109, that's the tetrahedral, 0.5 degrees. Now, you have a lone pair, the lone pair will squeeze the angle, will be, the angle is here, between nitrogen, hydrogen, nitrogen, nitrogen. So the squeeze is tetrahedral, 4 units for domain, but it will be squeezed. This is 107 degrees. Correct? How about H2O? I have 2 sets. It will be squeezed further. The angle is 105. Now, how about here, the theoretical compound we put? So what will be the angle here? 100 what? Around 103 degrees. So the more you have, the more lone pairs you have 2 effects. The polarity will go up, but the angle of within those atoms, with the central atom, will be less. Are you following me here? So we said the more, we said this one here, correct? Now we have this one here somewhere. We'll say the more you have lone pairs, the smaller the angle. So let's put this one here. The more lone pairs found on the central atom, the smaller the angle. So you can look at this. The H2O is 105 because but it has 4 units or 4 groups. 2 sets of lone pair and 2 sets of bonding pairs. So, but still, because of the 2, it went down. So the tetrahedral 4 units is 105. No lone pair. You get more lone pairs, the angle will be less and less and less. If you have a more theoretical compound, it has 4 sets. Okay. So those 4 sets even will squeeze the angle maybe around maybe 90 or 100 98 or 100 degrees. Are you following me here? Two issues of those lone pairs. They will force the molecule to be polar, and they will force the angle to be less. It will be more polarity, less angle degrees. Okay, guys? So, can I take this one out? Take it out? Okay, let's take it out, and then let's look at the so the angle will be what? About, we said that it has 6, so it will be, if you look at the chart I gave you, this one does not have the degrees, but I'll send you one with the degrees. I think the one with the degrees, you have it there. Just look at the another chart here of the lab. Let's look at the lab. I think the lab has some chart with the angle. Here it is, guys.
If you scroll up a little bit more,
What's that?
if you scroll up a little bit more, there's the degree, the angle bonds, degrees.
Yeah, I saw it somewhere here.
Yeah.
Yes.
So it's 90 degrees.
Yes, that's about 90 degrees. Yeah, that's just estimation there. So you can see those two sets of lone pair will squeeze the angle less. So let's take the second one. Let's take the second one. Where is the experiment here? Let's take the second one. So the second one, let's take the second one. CH3Cl. CH3Cl. What's the total valence electrons? Total valence electrons. I'm doing the second one here. Well, guys, this one here, this one, take it out. That's polar. This is polar here. First of all, it's an ion, correct? It's a charge, correct? So take this one out and just write polar. All the ions are polar, correct? They are ions, so how come they be ion? Because they are dissolved in H2O and they produce ions. So that's polar. And it has two sets of lone pairs. So how about this one here? Carbon, CH3Cl. One carbon, this is 1 multiplied by 12. And then 3 hydrogens, 3 multiplied by 1.00. And then 1 chlorine is 1 multiplied by 7. So this is 12, 3, and this is 7. So how much is this? Total is, valence electron is 22. 22, correct? 22. So now we have to lose that structure because we will know from there the non-bonding and bonding one. So from there you can tell hydrogen are always terminal. Hydrogen cannot because it has valence electron. Yes?
I thought carbon was 4.
Oh, 4, it is? Oh, the valence electron. Yeah, that's correct. That's correct, yeah. Yeah, well. Yeah, that's 4, that's 4. I'm wrong, you are right. So this is 4, this is 3, this is 7, this is 14, yeah. I'm wrong. I took the molar mass of it, atomic mass of it. That's 14, guys. Yeah, thank you. Somebody is awake, somebody is following me, somebody is awake. That's good, excellent. Yeah, this atomic mass is 12, and the this is in the 4th group. Valence electrons equal the group number. It's group number 4, so is 4. So now, when you look at this, the central atom has to be what? Carbon, because that's the least electronegative. And hydrogen is always terminal, you like it or not. You cannot put it in the middle of the molecule. So it will be, carbon is here, carbon is here, chlorine is here, 7, another chlorine is here, oh, 1 chlorine, correct? Yeah, 1 chlorine. Yeah, and then hydrogens. 1 hydrogen, 1 hydrogen, 1 hydrogen. So this is the code is, or the VSEPR formula, AXXXX. So this is EAX4. Low lone pair, no lone pair. Is this polar or non-polar?
Polar.
Non-polar or polar?
Polar.
It is polar. It is polar. It is polar. Correct. This is polar. If I convert this one here to H, that will be not polar. Correct? Because that's symmetrical. All the terminal atoms are the same. Correct? That will be polar. So this is polar. That's correct. Now, what will happen here, because we have no lone pair, the electron and the molecular shape are similar, identical. And both of them are tetrahedral, believe it or not. Because you don't have, they will differ if you have a lone pairs. So electron shape or geometry will differ from molecular shape or geometry if you have a lone pair at the central atom. If you don't have, they are identical, they are the same. So electron geometry is tetrahedral for both, and the molecular shape is, or geometry is tetrahedral. And the angle of the tetrahedral is around 109 because it has 5 degrees. Polar, yes, it's polar because this one here has different electronegativity from the carbon. Those dipoles will cancel those dipoles will cancel themselves out. But then you have this, all will pull all the molecule towards this, toward the most electronegative chlorine, correct? So guys, that's I think, and you have no non-bonding. So you have all these 4 sets of bonding, single bond. Can you do this one here, structure? Let's do it together. Let's do it together. Let's do it together, at least until the ozone, and then we'll stop. You can do the model then later. So you need 4 sigmas, 4 long ones. So you need the carbon, carbon, and we're trying to get this, and 3 of those. Bless you. And take a picture of your model so you can put it in the discussion. Make an image, please, and put this one here in your discussion. So if you don't have those images, I'll return that back to you. I need to see that. Yeah, take a picture of that.
So we have to do it here, so we don't have it at home. So
What's that?
we don't have this thing at home, so we have to do it here. Right?
Yeah, we have to do it here. But until the ozone, the other one, until the ozone, the first set. So we have the first set to what? To ozone, I think. Let me see where it goes. Yeah, to the ozone, and then BRF3, which is the same one. So there's some tetrahedral. This is tetrahedral, the last one. So it will be the same. So tetrahedral will be the same. Correct? Yes.
Will this be considered a double bond for CL, or is it still a single bond?
Well, the double bond will be shorter. Yeah, so don't take the shorter one, take the longer one. Here, I'll show you. Mine is here. So those are 3 hydrogens. See here? That's a tetrahedral. The chlorine is big than the carbon, correct? And those hydrogen is the smallest one. So this is a tetrahedral. Can you see it? So this is a tetrahedral. Chlorine at the top, carbon here, and those 3 green ones are the hydrogen. Yes, take a picture of it and add it to the discussion. We need just the first set. 1, 2, 3, 4, 5, I think 6. Just 6 models we need. We need 6 models. So make a picture of them. So that's mine here. I did mine here. So here it is. That's tetrahedral. Now, don't take it apart. Don't take it apart. This picture here, you can add it to the last one, BRF3. BRF3 is tetrahedral as well. BRF3 as tetrahedral, although the number of the size of the atoms are not equal, but the same thing. So fluorine is a small molecule compared, a small atom compared to bromine. So, but then you have 3. Here it is. 3 here. The last one. I'm looking to the BRF3, the last one. This is the fluorine atom. and this is your correct, your bromine. So is this PRF3? No, that's not the case. That's only like this. Here, guys, take this one here like this. Take this down. That's tetrahedral, correct? This is trigonal planar. That's not before, correct? That's not before. The last one is like this. The one we did looks like this, tetrahedral, correct? The hydrogen, 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 and the chlorine. Take the chlorine out, and this is the fluorine. This is trigonal planar, trigonal planar. This one is what? Trigonal planar, which is non-polar. Why is non-polar? Because you have identical what? Identical terminals. So this one here, let me take this one out. So this one here first. We did this one here. So we did this polar, correct? Let's do the last one. Let's do the last one here. The last one is trigonal planar. So it will look, yeah, this one here, I'm looking at this one here, guys. Trigonal planar. So this one here, I'm looking at this one here. The whole thing will be looking like this, I think, unless I'm wrong. So let me see. But it does not look like the one we are sitting. That's 3, correct? So, but how many for those are 3, correct?
Yes.
Well, then we have how many sets left for bromine? How many sets we have? BR4. I think that's a typo. It should be BR4, not 3. But anyway, so this is one for the bromine, 2, 3, and then no, that's correct. That's 4. That's 5, 6, 7. Well, that's not what I showed you. You have to have 2. That's not what I showed you. Lewis, that structure would say that this molecule has 2 sets of lone pair. It has. Let's do it here and then see what the shape of it. Just hold on. I can't do it for you because I don't have this lone pair. I'm missing a lot of stuff. So this is A, X, 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 and then E, and then E. So this is A,
X3.
X3, E2. Correct? Let's go and look at our structure here. AX3E2.
This one like that?
Yeah, that's 3. That's correct. Yeah, take a picture of it. Yeah, that's correct. But I want to see what the name of the shape is. So let me take this one here, and let me look at the shape of this. So where did I show you here? Here it is. Let me take this one here out. So we have AX3E2. Where is A? How many? The whole thing is 5, correct?
Yeah.
So we have 5 groups. So A, X3,
T-shape.
E2. So
T-shape.
will be a T shape. Now, don't tell me that's not polar. That's a typo. It has 2 sets of lone pair. It has to be polar. Anytime the central atom has a lone pair, is polar. So this one here, the shape of this, the last one we are doing it, so is, if you look at this, it's is here. 2 sets of lone pair and 2 sets of lone pair, 2 sets, and 3 terminals. Okay, that's T shape. Now, if you look at the five groups, the electron shape will be different. The electron shape is trigonal bipyramid. Trigonal what? Bipyramid. Trigonal what? Bipyramid. Trigonal bipyramid. Okay, guys, trigonal bipyramid. That's electron. It does consider this lone pair. But the other is T shape. And I don't think they will ask something like this because you can't memorize all the stuff. They have to give you a table. Otherwise, they will give you something very simple, H2O, ammonia, something like this. Okay, guys? This is T-shape. So, let's go and look at the, we have, make a picture of that, guys, make a picture of this. We have BF5 and O3, and then we'll call it off, and you can do the rest. The rest you don't have to do model, but you have to total of valence electrons, lose that structure, and you can do the polar or non-polar, correct? So here it is. Let's do BF5. The BF5, you can calculate the total. You can calculate, bless you. So you can calculate the phosphorus is you can look is 31. That's the is in group number 5. Valence electron is 5. 31 gram per mole atomic mass is 5, and the fluorine is 7. 7 multiplied by 5, 35 plus. Yeah, it's 40. Yeah, it's 40. That's the total. Total is 40. Now, this is will be looking like this. And if you look, a very unique that we don't have, because phosphorus has 5 valence electrons, are those, all those 5 are occupied, shared by the fluorine atom, correct? So this one here will be A, this is A, this is X, 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 that will be A, X5, no lone pair. So the molecular geometry will equal what? Will equal the electron or electronic geometry or shape, because there is no lone pair, correct? And as you can see, this looks like triangle, correct? Look at this. That's the base, and there's just, and if you look at the degrees, it will be different. So here is linear, 180 degrees. 180 degrees, linear. That's in the horizontal one. But then if you look at this here, that's like triangle, that's around 120 degrees. So those type of molecules will have within themselves two angles, correct? The question, it is polar or non-polar? What you can tell me about this? All those are the same terminals. So will be what? Symmetrical. Symmetrical means non-polar, correct? You get the idea. This is non-polar. If your lab say that's polar, just ignore your lab. That's a typo. That's non-polar, correct? And the angles has two angles. The angles are 2, so we can test the angles here. Let me see. This the angle is triangle, so let's see if I'm correct or not. But that's two. It has 2 angles. So let me check here. Everybody has this. Everybody has this. Okay, guys. So they have 5 domain of 5 zones. So yes, make a picture of it. Put it on the tab. Make a picture of it and add it to the discussion. If you don't, then I can't give you a full grade for this, because we have no lab. At least that's the minimum lab you can do. Make a model and take a picture of it. Not all of them, just the first 7 ones. So let's look at the angle here. I'm just looking up. We had those angles correct inside. So we say the 5 one, 100. Well, 120 and 180. It should be not 90. That I doubt, because this one here, look, this is 120. 90 is, well, she took this one here as 90, and then here as 120. But I take, well, that cannot be taken because it hits the two. Yeah, 120 and 90. But some of them 190, 120 and 180. Like the linear one, like this one here. I can show you. But anyway, so the angle is 120 and 90. So some of them, they have, let me just show you here. Oops, sorry. Yeah, if you look at this, some compounds here, I think I gave you here. Yeah, something like this. This is here, 4 sets, that's a linear. See here, the last one here, this one here. The angle is 180 here. It is 180. Okay, guys? Let's do the last one, ozone, and then we'll call it off for today. And you have to do the rest without, we'll do the last one. We'll do the last one, guys. We'll do the last one. So, let's do the last one. So, we'll do the last one here, ozone, correct? We'll do ozone. Well, ozone tends to be has 3 oxygen, and it's not stable because those oxygen is the same electronegativity, they will start fighting themselves. So I put one ozone in the middle, one oxygen here, one oxygen here. Each oxygen has to be satisfied with the octet rule, correct? So let's put this one here, double bond, for example. This one here, octet rule. This one is 8, 4 and 4, 8. This one here is negative. And this one here is 1, 2, 3, 4, 5 positive. This is the Lewis dot structure of ozone. This is what? The Lewis dot structure of ozone. Okay, guys? Now, this will be, you have to watch. This will be, let's watch this. What is the formula, VSEPR formula or code? This is A, this is X, this is X, this is E. So this is AX2, E and EX2, sorry. And E1. So my intuition will tell me this is what? This will be bent. This one will be bent, correct? This one will be bent. This is the molecular shape, the molecular geometry here. But since it has 2 plus 1 electronic or electron shape, the electron shape will be trigonal, because three units, 2 sets of bonding sets and 1 non-bonding, trigonal planar. Now, is it polar or non-polar? Polar. Why? Because it has a lone pair there. It's polar. And the trigonal planar, actually the degree is 120 degrees, correct? But since you have this, this will squeeze this one further. Maybe this one here, the angle is less than 120 degrees, maybe around 118 to 115 degrees. I don't know. You can check the literature of it. So, any questions so far? So your homework is, without doing the models, but let's do this model here. You have oxygen in the middle, and then you have 1 double bond, small, the smaller one. It is the smaller. So you have 2 of them. One is smaller. This is the smaller one, and this is the longer one. So you can compare. This single bond is double bond, and then both of them the oxygen connected to the oxygen, the same atom. So you might take the three atoms, the same one, the 3 atoms, the same size, the same one, correct? And 1 lone pair in the top, 2 of them, and then 1 pair in the top, and the angle will be squeezed less than 120. So the electron, consider the double bond is trigonal planar, 3 units, 3 zones, 3 groups, 3 domains. But the molecular one takes this lone pair out of consideration, and it will be looking like a bent, like H2O bent. Okay, guys? I think that's all. If you have any question, Any question? Yeah, that's 3 of them, but do you have the lone? Yes, that's correct. Yes, yeah, but where's the lone pair?
One lone pair, one.
No, no,
Okay.
no, it's not like the local.
Oh, a
Oh,
lone.
no.
The lone pair, it has a lone pair.
Yes.
It is?
Yeah, but that's 2, but where's the lone pair?
Yeah.
Oh, this one.
Yeah, there is 2 oxygen, 1 lone pair.
Yeah.
Oh, yeah.
Yeah. Yes. Well, I have to switch from. I have to. So any question you have? No question. So the homework is, just hold on. The homework is here, guys. So I told you here. Finish up those 1, 2, 3, 4, 5, 6, 7, 8. The rest of those. If you have any doubt or any question, email me. Email me, and you can check your Lewis-Dot structure with the literature in the web, correct? Or ask me how to do those. So, because it will take more than 1 hour to do all those together. Any other questions you have? If you have no question, then I will stop. You have to provide me in the discussion the first 7 ones. 1, 2, 3, 4, 5, 6, 6 ones. 6, are they 6? 6 ones. And the rest from the ammonia to the first page. Those you don't have to provide me any picture, any model. Those that second page, no. Just the Lewis-Dot structure. You can Google the Lewis-Dot structure if you are in doubt, or email me. I'll give you the answer for that. The main thing is you know whether they are polar or non-polar, correct? And the estimated angle between those given to you. Okay, guys. So let me stop recording here. That's it.